All right, so we've got everything in the universe. It's made by the Big Bang. But if you looked around after the Big Bang, the only two elements you would see are hydrogen and helium. You don't have all the rest of the elements like carbon, oxygen, nitrogen, iron, all the things that make us up, all the things that make up the Earth. So this is another detective story taking place over long periods of time. When people always wanted to know what stuff was made of, and so they would break down objects into their fundamental parts. And the 19th century chemists isolated elements with different properties and combined them and uncombined them, and they discovered simple relationships among them. And then in the middle of the 19th century, Mendeleev put all this together in a systematic way in a periodic table of the elements, where these vertical columns were atoms, elements that had certain similar kinds of behaviors. So sodium and potassium make salts, and they make salts with chlorine and fluorine that are over here on the right. And so this was gradually filled in, and everything was made up of all the elements, and matter could be neither created nor destroyed. Once you had the pure element, you couldn't break it down into anything else. You could only that was it. You could combine it with a bunch of stuff, but you couldn't break it down. So where do the elements come from? Those are all the elements, but this big question, where do the elements come from and how were they formed? You would have been taught a chemistry class in the 19th century showing this great discovery of the periodic table. You're taught the periodic table in chemistry classes today. But where do the elements come from? And why do they have this kind of organization? So this was a great mystery, though not one that was much worried about because nobody could figure out how to determine the answer. And then there were people who were looking at minerals that emitted a certain kind of radiation. And they were interested, like fluorescent minerals, you expose them to sunlight, and then you shine a black light on them and they glow and they're incredibly pretty. And they discovered a mineral called pitchblende, which seemed to be able to expose photographic film. And so Becquerel thought, okay, I'm going to examine these kinds of minerals, and I think they get their energy from the sun, so I'll expose them to sunlight, and then after exposing to the sunlight, I'll wrap them in photographic film and see how much radiation they absorbed and how much they can emit. And he had one mineral. There was a cloudy day, I guess, no sunlight. And he thought, he had this one mineral, and he thought, okay, that wasn't exposed to sunlight, but it'd be good to know what the background is, what the noise level is, so I'll wrap that in photographic film. And he wrapped it in photographic film, and it was fully exposed. No exposure to sunlight, but fully exposed. So, okay, let's take this mineral. I'll leave it in pitch blackness for a week, and then I'll wrap it in film. Film was totally exposed. So this object was emitting something from itself, not something that it absorbed from the sun. It was emitting some kind of radiation. And it turned out the radiation that it was emitting could cause noise in electrical things. It could be bent by a magnetic field. It was a particle. It was something. And Marie and Pierre Curie then worked with this, and everybody figured out that this radiation was coming from the element uranium. But Marie Curie, in looking at it, realized there must be something much more active than the uranium in these rocks. And she was then able to separate a much more radioactive element called radium. And radium was a gold mine because it was so radioactive that uranium just emits a little bit of radiation, but radium emits, tens of thousands of times more radiation than uranium. I don't know what the exact number is. And so this provided a radioactive source that could be used for various kinds of experiments. Marie Curie is one of the greatest scientists ever to live. She's the first woman to win a Nobel Prize, and she won 2 Nobel Prizes. So this stuff that was being emitted could be bent, and the particles that were coming off it, just because they were the first particles that were discovered, were called alpha particles. And so what would happen if we created an alpha particle gun, because it could be focused using a magnetic field, and we shot it at different elements? What would happen? So Rutherford did this. He put some radium in a box and focused it and put very thin gold foil and had a detector on the other side of the gold foil to see what happened to these particles. Did they bounce off? Did they go through? What happened? And to his and everybody else's surprise, almost all of them went through. Shoot them through solid gold, very thin solid gold, but solid gold, and they go through it as if there's nothing there. Now, every once in a while, one would be bent or one would bounce back, but almost all of them just went straight through or were just slightly deflected. And this led to the concept that atoms are mostly empty space. So you have an atom, it has something in it called a nucleus, and it's surrounded by empty space, and those are where the electrons are, and this is where the protons and neutrons are. And so the nucleus is this tiny thing, and so when you shoot particles at it, which are little particles similar to what's in the nucleus, those particles mostly just go straight through. Every once in a while they come close to the nucleus, and so they're bent because they have the same charge. And every once in a while they hit it and bounce back. But that's a very small number of them, and in this way you can determine how much of the atom is empty space and how much of it is the nucleus. And almost all of it is empty space. So if you take your fingernail, and your fingernail were the nucleus of an atom, the electron cloud extends to the Boston suburbs. The nucleus has almost all the mass of the atom, but it's the size of your fingernail. Or if you made the nucleus the size of the science center, the electron cloud's the size of the Earth. You're made of nothing, right? Everything is made of absolutely nothing. Just empty space. It took a long time, but they discovered that the nucleus was not just these protons, positively charged things, but it was also made up of neutrons. And then much later, with higher energies, people discovered that each proton and each neutron is made up of still smaller particles called quarks. And the neutron and proton themselves are almost entirely empty space. These quarks are really, really small. And so you have the nucleus, which is 10 to the minus 15th meters, and the quarks are more than 10,000 times smaller. So you have the atom, it's nothing. The nucleus is this little tiny thing. And you take the nucleus, and it's nothing. It's just made up of these little tiny particles that are even smaller. Amazing how all this nothingness is so interesting. So immediately after the Big Bang, the temperatures are so high, you only have these smaller particles, just these fundamental particles that are so tiny. And of course, that's the reason why so much stuff can be packed into a small space, because the universe is essentially nothing. And so you can put a lot of nothing into a very small volume. And then the universe passes from this to, which is a state of incredibly high energy, completely unfamiliar to us, to the collection of elements that we have today. And the simplest of these elements is the hydrogen atom. It has one proton, positively charged, surrounded by a neutron, surrounded by an electron, negatively charged. You understand, I can't draw this to scale. If I showed the electron going around the proton, there would be nothing there. It would be so tiny you couldn't see it. So we have to depict it like this, saying there's this proton. That makes you think a proton is something big, but the proton is actually this incredibly tiny little thing. And the next element is the helium atom, and it has two protons, and 2 neutrons. The identity of the element depends on the number of protons. So hydrogen is a 1-proton element, helium is the 2-proton element, and as you go up the periodic table, the number of protons determines the identity of the elements. Of course, this is also not to scale, because it has 2 positively charged protons, it has 2 negatively charged electrons circulating around it. But you look at this, and you'd go, whoa, whoa, that's impossible. You can't possibly do that. Because look, those 2 positive charges are right close to one another, and they're going to repel each other. So since they're going to repel each other, this can't hold together. The nucleus should completely fall apart. So you can, here's 2 magnets. So here are the 2 red parts, or the positively charged parts. And you can try to put them together. Go ahead. You're going to put them together. As you get closer and closer together, it's very hard. What are you, completely incompetent? Can't you just put those 2 things together? You'll see everybody's incompetent like that. The repulsive power of magnetism is huge. And the power of magnetism is very great. Here I have a magnet, and this is pretty heavy. It's being held by the Earth's gravitational field. So the whole gravity of the Earth, the massive Earth, is acting on these nails to keep them in that. And so I'll take a magnet and pick them up. No problem. It's fantastic. Fall off, you. God damn it. Fall off. No matter what. Oh. I'm supposed to, so the next line is, no matter what I do, I can't get them to fall off because the electromagnetic field is so great. Or I can easily, pick up anything with a magnet. Or the magnetic force is, here's a magnet on a spinning thing. So if I like magic. Yeah. So look at this. Just one little pulse from this magnet. And you can make it spin. So these are little magnets. So you can try to take them apart, okay? So you just take them off. Okay. Try to put them back together again. Don't put it near your cell phone. So 5 magnets. So whoever can take these magnets and pull them, more than one of them apart, gets a free ice cream cone. But don't put them near your computer or near your cell phone. The magnetic force is incredibly powerful. It's so much more powerful than gravity that a little tiny magnet is able to counteract the force of gravity. So here's a small magnet. And it just picks up that paper clip. Just picks it up. Right? Okay, another failure. Okay. Or I could take this magnet and pick up this whole box of paper clips, but then it would take me a long time to get all the paper clips off of the magnet. So the power of electromagnetic repulsion that is pushing these little magnets that are in the nucleus apart is incredibly great. And you can measure its power compared to gravity. So here's gravity. It's 6 with 39 zeros in front of it. And there's the electromagnetic force, which is a 7 with just 2 zeros in front of it. So 39 zeros, 2 zeros, that's 37 zeros. That's 10 quadrillion times more powerful. And that's why the magnet, this relatively small magnet, is able to counter the gravitational force of an entire planet. So in order for the nucleus to hang together, there has to be a force that is stronger than the electromagnetic force, even though the electromagnetic force is so powerful. And so the strong force that holds the nucleus together has a value of 1, which is a little more than about 142 times stronger than the electromagnetic force. And that force is like a kind of nuclear glue. It only operates when you can put two things together and have them touch. And then there's like a super glue, and so the physicists, with their great sense of humor, have a name for the particle that does that. They call it the gluon. And the gluon is the way the strong force acts, but it can only act if you can bring two nuclear particles together and have them touch. And when they touch, then it's superglue. So if you take those two magnets that I gave you out there and you try and put them together, and you somehow manage to get them to touch, and they had instantaneously acting superglue on them, then they'd stick together if the superglue was 100 times stronger than the electromagnetic force. So that's the way the atoms can stick together. And then we can start to talk about how you make more elements. You have hydrogen, which is the first one, helium, which is the second one, lithium, which is the third one. The identity of the element is controlled by the number of protons. Those are the red balls. So hydrogens always have one proton, but they can have 0 neutrons, 1 neutron, or 2 neutrons. And if they have 1 neutron, then they're 2 nuclear particles, so you'll put a little subscripted 2 to the left and above the hydrogen letter. And if they have 2 neutrons, then they have 3 nuclear particles, so you put a 3 superscripted. And helium always has 2 protons, but sometimes it has 2 neutrons, sometimes it has 1. Lithium, the next element, has 3 protons. Sometimes it has 3 neutrons, sometimes it has 4. And in this way, you can build up all the different kinds of elements. And we build them up on something called the chart of the nuclides. And that has the number of neutrons on the horizontal axis and the number of protons on the vertical axis. So hydrogens all have 1 proton. They're all on this line. And helium all has 2 protons. They're all on this line. But you can have different numbers of neutrons. And so you can have hydrogen 1, hydrogen 2, and we don't have hydrogen 3 on here because it's radioactive. It's called tritium. And when you have these individual boxes, each one of those individual boxes is called an isotope. So hydrogen has 2 stable isotopes, hydrogen 1 and hydrogen 2, and 1 radioactive isotope, hydrogen 3. Helium has 2 isotopes, helium 3 and helium 4. Lithium has 2 isotopes, lithium 6 and lithium 7. They're both elements, they're both lithium, they both have the same kind of chemical behavior. So isotopes of an element have the same number of protons and different numbers of neutrons. And an isobar is when you have exactly the same total number of nuclear particles. So that's horizontal 45-degree lines on this diagram. So if there were something out here, it would have 4 neutrons and 0 protons. This is helium 2 plus 2. If there were something up there, a lithium, it would have 3 protons and 1 neutron. Yes?
Why wouldn't you be able to synthetically create an infinite amount of isotopes of a single element?
Any isotope?
So like the hydrogen, for example, like with hydrogen, you were saying it just has the difference between the isotopes is the number of neutrons.
Yes.
And you said that it goes from hydrogen 1 to hydrogen 3, which is radioactive. But why wouldn't you be able to like say synthetically create hydrogen 4?
Because it would be radioactive in decay. So when you look at this chart of the nuclides, there's sort of a diagonal set of boxes on it. Those are the nuclides that are stable, that are not radioactive. And anything you made that's outside of that band is radioactive. And when it's radioactive, it decays back to the band. So things that are out here decay up that way, and things that are up there decay down this way until they get to this band where the stable isotopes reside. Are we okay? All right. So what's going to be determining nuclear stability? And that's going to be Einstein's famous equation. You thought that was physics, but it's also chemistry. So the energy is equal to the mass times the speed of light squared. Speed of light squared, speed of light is a big number, so the speed of light squared is a huge number. And if there's a loss of mass, then energy is released. And if there's a gain in mass, energy needs to be added to make the reaction happen. So if you want to convert something to higher mass, you have to throw a lot of energy into it. And if you take something and you let it react and its mass decreases, it's going to be releasing a lot of energy. And it's all related to that equation. So when there's a loss of mass, the reaction is downhill. It's like a ball rolling downhill. Gain of mass is rolling uphill. Loss of mass is rolling downhill. As long as there's a loss of mass, the reaction happens. When there's a gain of mass, it can only happen if you put energy into it. So if you look at the mass of the neutron and the mass of the proton and the mass of the electron, you see that if you add proton plus electron, it's 938.791. And if you look at the mass of the neutron, it's 939.57. So that's a bigger number. And therefore, the neutron left to itself is unstable with respect to being a proton and electron. And any neutron that is on its own decays because there's a loss of mass and makes a hydrogen atom, which is the proton plus the electron. Where's the question?
So with the equation, like E equals mc squared, will you actually physically lose mass or will mass just go
Yes.
somewhere?
It's conservation of energy. And mass and energy are convertible. So the mass goes somewhere, it goes to energy. It doesn't go to another mass somewhere. That's the magic. In normal chemistry, in planetary processes, in the periodic table, there's conservation of mass, and it's an inviolable law. But when you're dealing with nuclear reactions, that's no longer true, because mass and energy are convertible to one another. If you look at the mass of 4 hydrogen atoms, they come up to that 6.96. This is different units now, sorry. And if you look at the mass of 1 helium atom, it's a smaller number, 6.648. So that's a mass loss of that many number of grams. You multiply that by the speed of light squared, you get a huge amount of energy. So if you can take 1 gram of hydrogen and convert it to helium, that releases enough energy to boil millions of pounds of water. So how cool would that be? If we were able to do this, you could take a mass of hydrogen the size of a sugar cube. You could put it in your basement in your hot water heater, and you'd have all the hot water you would want for your entire lifetime. You never have to use gas. You never need to be connected to the grid. You just have this little tiny thing of hydrogen, and it's making helium gas and releasing it and giving you hot water forever. It'd be totally wonderful. So why can't we do that? We can't do that because that reaction happens only when 2 hydrogen atoms touch one another. When they touch one another, then the gluon can act, the reaction takes place, the mass is lost, and energy is released. But how do we get those 2 damn things to touch? So do you have those magnet sticks? So could anybody get, oh, you got 2 off. Okay, free ice cream. You should collect. These little magnets are neodymium boron iron magnets. Have you heard of neodymium? Neodymium is one of these rare earth elements. And you know all about the big problem with China? That you need rare earth elements to make magnets and for all kinds of important things, for things like cell phones. And China basically has a monopoly on rare earth element deposits. And so when they were having a dispute with Japan, they said, okay, we're not going to give you any more rare earth elements, which would have completely crippled the Japanese technology industry. So these little tiny elements can be really important. Okay, so as you saw, these are hard to put together, right? Ha! So if I get them moving fast enough, I can get them to touch. And if I had a super glue, I can't hold them together with my hands, but if I had a super glue that was 100 times stronger than I am, all I'd have to do is get them to touch, and then they would be stuck together. That's what happens with nuclear reactions. You just have to get the atoms moving fast enough that they can touch. And if they touch, then if there's a loss of mass, they spontaneously react and release all this energy. That's hydrogen fusion. That's what happens in the sun. Because you can get up to 10 million degrees, that makes things move fast enough that these nuclear particles can touch one another, and once they touch, they can react. So you have this situation where you have two protons indicated up there by those little yellow balls, and as they get closer and closer, they repel each other more and more. They can't touch. But the strong force begins to act, provided they touch. They get very, very close to one another. And then when the strong force acts, then nuclear fusion can happen and the energy is released. So that's why with a hydrogen bomb, you have a uranium bomb surrounding it. And so the uranium bomb goes off first, and that creates the 10 million degrees temperature. And it's also keeping the hydrogen together, so the hydrogen is imploding. And that makes the hydrogen atoms touch, and that then allows them to fuse, and that creates the much larger hydrogen bomb, which can destroy vast cities in a few seconds. You need these really high temperatures for, so that was a great, that was an amazing technological achievement to be able to create high enough temperatures that you can lead to hydrogen fusion. And that's the big challenge with fusion energy, is how do you create circumstances where without creating a hydrogen bomb explosion, you can get a small number of hydrogen atoms to come together and touch. For that you have to create very high pressures and very high temperatures in a volume. So you have to create this domain where you get millions of degrees and you can fuse the hydrogen atoms, and then you have to get, that takes a lot of energy, and then you have to get more energy out from doing that than you put in to make it happen. And that's why it's such a technological challenge to make fusion power actually work. Now this only works if there's released loss of mass. Then they stick together and they release energy. If there's a gain of mass, they won't stick together, because then you have to put energy into it to make it happen. All right, so the total mass of a nucleus depends on its energy as well as the number of protons and neutrons. Protons and neutrons weigh different amounts in different atoms. It's weird. They don't have like a, you're not just putting them together like billiard balls, they actually weigh different amounts. The mass and the energy are convertible. The neutrons all by themselves convert to a hydrogen atom, and nuclear fusion happens as long as the mass of the reactant, of the product, the thing that's being reacted to form, is lower than the nuclei that are reacting. But for that to happen, you have to get the nuclei to touch, and this requires extremely high temperatures. So what happens during the Big Bang? It's expanding. So that's cooling. Everything's cooling off. It makes neutrons. The neutrons convert to protons. The hydrogen atoms, some of them fuse to make helium atoms. So you're making hydrogen, but helium is a little bit later in the production process. So you make a little bit less helium. And then you have this amazing situation of the way the universe is organized. Which is that at the 5 isobar, there's no stable atom. There's no stable isotope. So here's the 4 isobar. You see at 5, there's no box. And you have 6 and 7, and at 8, there's no box. Why is the universe set up that way? Why no 5? Why no 8? What's the point? It's weird. Well, that's what makes later stars possible and makes life possible. The fact that you don't have stable isobars at 5 and 8. So you've got your helium-4 that you made, and it could fuse with a hydrogen-1, but that's equal 5. Doesn't work. You could have a helium-3 healing with a hydrogen-1. That makes helium-4, but then that can't go to 5. You could have helium-4 fusing with itself, but that's 8. No dice. So there's a bottleneck. You can make hydrogen and helium, but you can't jump over this double trap. You have to jump over a double trap to be able to make the heavier elements, and you can't get over it. You can make a little bit of lithium, you can make a tiny bit of beryllium, but basically you're pretty well stuck by only having hydrogen and helium in the ever-expanding universe. So then how are we going to make the heavier elements? So as the universe is expanding, there are domains where things are contracting. And so as the cloud contracts, as anything contracts, it heats up. It keeps contracting, it keeps heating up, it gets hotter and hotter. Gravity is holding it together. It heats up, it gets hotter and hotter. Gravity is holding it together. It keeps contracting, it heats up, it gets hotter and hotter, reaches 10 million degrees, and kabam, hydrogen fusion happens. Now it's generating heat by fusing hydrogen. When it generates heat, that heats it up, that makes it expand. So the heat is making it expand. The gravity is making it contract. It's pulsing. It's trying to contract by gravity all the time and being forced to expand by nuclear fusion all the time. It's in this state of steady state disequilibrium that we talked about for planets 2 lectures ago. And it lives in that state, balanced between the forces of gravity and the forces of nuclear fusion, which keep it in this constant state, if it's a small star, for billions of years. Now, the bigger the star, the stronger the gravity, and the more heat is required to counteract the force of gravity and to keep this star from collapsing in on itself. So, you can imagine then, if you have a big enough star, you have a huge amount of gravity pushing it in, and it heats up a lot, and you have to keep it from expanding, so you burn up all your hydrogen fuel. Now, what do we do about the mass trap at mass 5 and 8? Well, in the star, you're not expanding, you're contracting. And since you're contracting, you're forcing all these atoms to be together. And then you can force things so close together that 3 helium atoms can react. And when they do, 3 times 4 is 12, and you make carbon 12. We can define carbon as exactly 12, just to keep the unit simple. That the mass of 6 protons and 6 neutrons is 12.1, so there's a loss of mass. And so you can make carbon 12 if you can get the helium atoms to touch. This keeps going. You make more and more and heavier elements until you get up to the mass of iron 56, which it's 55.935, and the mass of 2 silicon atoms is 55.954. So you could fuse 2 silicon atoms together, and there's a very small loss of mass to make iron 56. That still happens. But since the repulsive force is very strong for these, iron has 26 protons, so the iron nuclei are really repelling each other. To get them to touch requires still higher temperatures. So the heavier the atom, the more extensive, the heavier the atoms that are fusing together, the higher the temperatures have to be. So what's going to happen is that you fuse hydrogen to make helium. That requires 10 million degrees. And then when you fuse helium to make carbon and oxygen, that requires 100 million degrees. And when you combust silicon to make iron, that requires 4 billion degrees. The temperatures are getting really hot. But then an amazing thing happens. We're so far going up a path like this where you're having mass loss as you're making all these elements. This is the atomic number. You have hydrogen down here. You have a big mass loss as you go up to make helium. And then you keep losing mass, but you lose less and less and less mass until you get to iron 56. And after iron 56, there's no more mass loss when you put atoms together, there's a mass gain. So when there's a mass gain, it does not happen spontaneously. So what happens is you have this star, you have little stars, like our sun, which burns hydrogen to make helium. It lives for a very long time. You have medium-sized stars that burn hydrogen to make helium and then burn helium to make carbon. And then you have the super huge stars that go on, and in their cores they're making silica to make iron. But then once the silica has fused to form iron, there's a very little mass loss, so you're not getting very much energy. And then there's no more fusion that can happen. And there's no more fusion that can happen, so there's nothing to keep the star from imploding in on itself. So it implodes in on itself, and all the atoms, all the nuclei get so close together that the repulsive power takes over, and it explodes spectacularly out into space. So you have two things happening. You have element formation, which is happening in the stellar interiors, and then you have element distribution, which is happening when the very large stars explode. And the very large stars, the gravity is so big that they have very short lifetimes and explode in 1 million years or so. So in this case, we've made all the elements up to iron. We've distributed through the universe. How do you get elements that are heavier than iron? Well, when you explode the star, you create lots of free neutrons. They have no charge. So when the free neutrons have no charge, they can just go in and hit the nucleus and they're not repelled. And so you're adding mass to the nucleus. And then those masses decay and make all the heavier elements in the periodic table. So how does that happen? We have this band of stability, but we have a lot of empty space. And what's happening in this empty space, if you're adding neutrons, you're moving out over here to the right. And you have a reaction down here, which is a neutron is able to convert to a proton plus an electron, just like happened during the Big Bang. And when that happens, you're reducing the neutron number by 1 and increasing the proton number by 1. So you're doing this. You're taking an isotope in a box out here like carbon-14. The neutron is going to convert to a proton. So as the neutron converts, you lose a neutron. The number of neutrons goes down by 1. And as you make a proton, you're increasing the number of protons. The number of protons goes up by 1. So you move along an isobar like this through radioactive decay, which is the conversion of one element to another element. So here's the grand chart of the nuclides, now going out to include all the different isotopes of all the different elements. And all these brightly colored things that are not red are the stable isotopes. And when you have a supernova, it adds neutrons all the way out here, and there's some free protons that are going fast enough that they can join two. Those go out here. And then once they're out in this region, they just decay back along an isobar until they reach a stable state. All of these red ones are radioactive. All of these colored ones are stable. So, thousands of PhD theses have then been done to create all these radioactive elements. I've now turned the band of stability on its side here. So these red and blue things and green things are all the stable isotopes. And these are all the unstable isotopes. And they would all react back to the band of stability. And as they do, they emit radioactivity. And they give off energy, and they give off the radiation that makes us so frightened. Some of these do that very slowly, and that's indicated by these little black boxes in here. Their identity is not so important. And uranium is one of those. It decays over billions of years. And so some of these things that are radioactive decay in milliseconds or microseconds. They just have very, very short lifetimes. But as they approach the band of stability, they get almost stable. And when they're almost stable, they decay very, very slowly. And those are the elements that are still present on the Earth, the ones that decayed very, very slowly. And they provide radioactivity that we can use. So here's the time frame for a massive star. This is a massive star, maybe 25 times the mass of the Sun. And it's burning hydrogen. It has a certain density here. Doesn't matter what these units are. And it's burning up in 7 million years. It's so big that the hydrogen burns up really, really fast. Our Sun is small enough that the hydrogen can burn slowly. But in the massive star, the gravity is so great that to keep the star from contracting, the hydrogen burns up. And then you have helium. Now helium, when it converts to carbon, there's less mass loss, so it's going to burn up even faster. And so it burns up in only 500,000 years. And then that makes carbon, and the carbon burns up in 600 years. And the neon burns up in 1 year, and the oxygen in 6 months, and the silicon in a day. And then it collapses, and in milliseconds it bounces back and becomes explosive on the time scale of seconds. And if you multiply temperature by 10 million, you get the temperature in degrees Kelvin. So up here you're talking about billions of degrees. And when these explosions go off, they're as bright as a galaxy. So here's a picture of the sky in 1959 showing a galaxy. And then a supernova went off here. And you can see that supernova is just as bright as the whole galaxy. They're emitting vast amounts of energy in a very short period of time. And when astronomers see them go off, then they can watch the decay of the energy as the various elements collapse. And here's another one. There's nothing there, and then you have this red dot that it's going off. These are galaxies. And then you can see them with time. So here there's supernovas that are expanding and sending all their elements out into space. And they make beautiful nebulas like this one. So this is, the size of the solar system in here is something really little tiny. So when these supernovas go off, there's these vast explosions in space emitting huge amounts of energy. And the Crab Nebula was one that was seen by Chinese astronomers in 1100 something, and it can be observed today, and it's expanding rapidly, and you can measure its chemical composition and see what's happening in it. These are the great superheroes of the galaxy, making all the elements and distributing them into space. Now I have some reason. So there's a couple of interesting details here that I think we'll go over some of these details next time because they're a little too much to explain at this moment. And instead we'll sort of conclude with the big story, which is last lecture we hit the Big Bang, and we now know that it happened 13.7 billion years ago. And then, over billions of years, supernovas go off in all the galaxies, and as the supernovas go off, they're making all the heavy elements and distributing them. And that takes a long time. So they gradually make more and more elements through universal history, and 4.7 billion years ago, our solar system formed, and it was able to make use of all these elements that were being made over the billions of years previously since the Big Bang happened. So as you make solar systems later in universal history, there are more and more of the heavy elements. Or as you go towards the center of a galaxy where there's much more energy and more supernovas, there you have a much higher density of the elements than you do out on the outskirts of a galaxy. And all these things come together, creating the elements that are going to be necessary for creating life and creating planets. And this process is occurring everywhere throughout the universe. And so when we look at the far-field image of the Hubble telescope, which is this thing where each one of those dots is a galaxy, The same elements are being made everywhere. The same process of supernovas is happening everywhere. All of it creating a universal environment which is going to be suitable for the evolution of habitable worlds. So the major point for habitability is we understand how elements form. It's a fascinating story having to do with the electromagnetic force and the strong force and gravity and steady state disequilibrium and understanding the chart of the nuclides. It has interesting complexities which are worth trying to fathom so you can understand how these elements form. It proceeds gradually by the supernova superheroes exploding over billions of years, seeding the universe with all the elements that are necessary for planets and life. And new elements are being made today in stars. We can see supernovas going off in the night sky every once in a while. Sometimes you'll see them reported in the New York Times or something like that. The supernovas are the way that we determine the distance to distant galaxies because they're so bright. And we know how bright they are, so we can use that to determine the distance to galaxies. And the same elements are being made by the same processes everywhere. And so there's this uniformity of universal process. And that's the sort of one of the central themes that I'm going to try to be continuing to develop through the semester, which is that the processes that we observe on Earth today are probably examples of a universal process. The Big Bang is everywhere. The elements are everywhere. The elements are made in the same way everywhere. The elements are present for all solar systems throughout the galaxy. We'll see later on that probably every star has a solar system. And so perhaps when we're looking at the processes that take place on Earth, we're looking at an example of a universal process that's taking place in trillions of locations throughout the universe. Yeah?
Is it thinkable that there are other elements in another galaxy or solar system?
No. Everywhere we look, the elements are the same. If you had multiverses, multiple universes, you could have other universes where you wouldn't have blocks at mass 5 and 8 because the physical constants